Hello, welcome back. In this segment, I will introduce you to the notion of a binary relation. If you are doing reverse engineering, oftentimes you deal with the relations among different entities. It could be one function calling another function or a class inheriting from another class. This is basically relation between two things. So I'll formalize binary relation and we can define operations on the binary relation. Let's take a simple example. Suppose you have a set of functions, right? Maybe main, run, terminate, or whatever. Functions often call other functions. So the call is a relation between two things, caller and callee. So essentially a binary relation is collection of pairs. Okay, you can represent binary relation with it as a table with two columns. Okay, you could put caller as one column, callee is another column. So this is caller, right? And this is caller table. This is caller and this is callee. So could be that main is calling run, then you have one row for that. Run may be calling something else, then they have another row. So let's just type one example, right? Main is the caller who's basically calling, say, run. Similarly, there may be many things here. Okay, so caller, callee, this is a binary relation because there are two columns here. Caller, callee, this is the word binary here, means two. And this whole thing, this table itself is called a relation. Okay, this is the relation. Let's call this table to be call table, right? Call.rel, for example, just to make sure that the idea of relation comes out. I wanted to call it call.rel. Okay. So call is a table with two columns. That's how you can visualize binary relations as a table. You can also visualize it as a graph. Every row is one edge. So in this case, main is one node and run is another node, and main calls run. That means you can draw an arrow mark from main to run. Okay, so the beauty of binary relations is that you can also visualize them as graphs, direct graphs. Okay, so you could apply graph analysis on this graph to extract knowledge. You can also do SQL-like queries on this table to extract data, extract new information, whatever. Okay, so this is essentially what is binary relation, which informally speaking. Yeah, I'll formalize it now. So binary relation requires two sets, A and B. They need not be different. They can be the same. A can be equal to B. So you need two sets, A and B. So what is binary relation then? A binary relation is another set R, okay, which contains elements from A and B. So we write it like this in mathematics, A times B. Okay, what is the meaning of times then? Times means you pair every element in set A with every element in set B. Anyway, let me finish this formalism. A and B are two sets. The relation is just a subset of A times B. This notation, this is called a subset contained within A times B. What is A times B? Let's take an example. A simplified definition of binary relation. I'm going to treat A and B are same. Okay, that means my definition of R will be R is some relation which is a subset of A times A, right? This is binary relation. This is also binary relation. The only difference is B and A are the same now. Okay, let's take this as an example and work out a scenario. Let's say A is made of elements 1, 2, 3, and I'm going to define R as follows. Say 1, 2 as a pair, 1, 3 as another pair, 2, 3 as another pair. As you can see, R is clearly a subset of A times A. What is A times A? A times A means 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So you can visualize it like this. Suppose you have 1, 2, 3 as A, and you again write 1, 2, 3 as another A, which is actually B. It doesn't matter. B and A are same. And what is the meaning of A times A? What is the meaning of A times A? You take this, you associate with everything here. For example, like this, like this. So 9, you'll have totally 9 pairs. That's all possible pairs, but the relation is just a subset. If you pay close attention, my R is a subset of A times A, and I have an interesting property in my R. I have only selected elements such that the first element is less than the second element. Yeah, you can see 1 is less than 2, 1 is less than 3, 2 is less than 3. So R is some relation I have defined among the elements of A, and I just made it explicit that it is less than. Less than is the relation in this case. But in reverse engineering, we don't usually deal with numbers. We deal with function names, file names, and so forth. So in that case, your A will be set of functions like main and run. Or could be, if a function calls another function, then you have that pair. That is your R. Okay, R is the call relation. Okay, hopefully the idea of binary relation is coming across. I will show you a binary relation calculator where we can do these things programmatically and visualize the output to get a much more clear understanding. Let's do that right away. Let's define very simple set made of main and run, and we will do times first, and then I will show you other operations. Let's say I'll create a notepad, right, with function names. Let's call it func.set. So I have func.set, and I'm going to define the elements, namely main and run. So I'm going to just create a few elements so that we can analyze the operations of relations. So main, run, initialize, I don't know, I'm just making up some examples. Exit. These are the set of functions. You might have extracted it from some parser, or by running the system, you found out these functions were executing for whatever reason. Okay, so it doesn't really matter. I have a set of functions. What can I do with this set? This is a special calculator, relational algebra calculator, but you will see the output very, very soon. Rel times operation. It is essentially multiplying every element of set A with set B. In this case, A and B are the same. As you can see here, init, run, init, exit, all possible pairs are produced. That is the idea of rel times. Okay. So in this case, we are seeing all possible pairs. These pairs may not call each other. We just have a list of function names, and we just did a cross product. In mathematics, we use the term cross product for multiplying two sets. Okay. And now let me define a simple relation between the functions. So here is your table that I was talking about, right? You have a bunch of edges. If you wanted to visualize it as a graph, main is depending on run, mains depending on submit, and so forth. Okay, so now you have this call.rel, and now we can analyze this. For example, identify the entry points, or identify functions that are only used by others, and that function is not using somebody else. Many things you could do once you have this table. And in reverse engineering, you have all these questions oftentimes. What are the entry points? Who is calling this? And so forth. We can formalize it as relational algebra queries. Once you have this relation table, you can do simple things. Let's find out who are the entry points. We have something called rel top in our calculator. It will tell us the entry point. It turned out to be main is the only function that is starting all other functions. That's naturally the entry point here. How was it possible to calculate the entry point? In the previous segment, I defined the set theory operators. You can imagine taking the first column of the call.rel table, taking the second column of the call.rel table, and performing a set difference. Okay. Identify elements that are present on the left-hand side, identify the elements that are present on the right-hand side, and do a difference between those two sets. Set difference between left and right of your table should be giving you the entry points. This is how you can find the entry points into your call graph or dependency graph or whatever. Okay, so rel top. I will define composition, which is something very useful oftentimes. You can compose two relations to form a new relation. Let's take a simple example, right? I have the call table where I have caller and callee. I'm going to compose this with another relation. Okay. Let me call the other relation to be part of relation. Okay. So you saw the call.rel table. Now I'll create another table, part of.rel, where we can just define where is main. Main is perhaps defined in main.c, just as an example, right? Run is run.c, exit.c, and so forth. So let's just keep this as simple as possible. I have defined these in a file called part_of.rel, as you can see. Now I will combine the call table and part_of table to show you the behavior of composition. Okay, so composition is actually easy to define as follows. Suppose you have relation R, let's call it relation R1, and you have another relation R2. I'm only talking about binary relations. That means you can imagine a table of two columns. R1 is a table of two columns, R2 is another table of two columns. What is the meaning of composition, right? So all you have to do, let's say, I'll define a new relation called composition relation R3. I'll denote it by R1 composition, R2. Composition is usually drawn with a small circle. So how do I do R1 composition R2? All I have to do is as follows. R3 will contain all possible elements xz such that, this line is called such that in mathematics, usually, such that x comma y belongs to R1. That means the first relation R1, the second column of the R1 table, has to have a y, and the first column of R2 has to have this y, z belongs to R2. Then we basically ignore the y and take x and z and put it into this pair. So this is how you formalize in mathematics. R3 contains all pairs x comma z such that there exists y such that x comma y is in R1 and y comma z is in R2. Then you have your composition. Okay, this is also called join in database world, but this is just combining two things to form a new relation. Okay, so maybe an example will help you. I'm going to combine call table and part_of table, right? Relcom is essentially the join, which will take two relations. In this case, I'm going to take call relation and the part_of relation. I composed it to form a new relation. So what you're seeing here now is dependency from function to file. Why do we have the dependency from function to file? The reason is as follows. Call is between function to function, right? Function to function. You have one function depending on another function that is in the call. Okay, so it's a bunch of function pairs. That's the call.rel. But what about part_of? Part_of is function with file. So if you join call with part_of, what are we doing? We are taking the second column of the first table. This is the second column. And we are looking at the first column of the second table. And if they are equal, if these two things match, then we connect these two things. That's the reason why you see a function and a file. Okay, so composition is just join in relational database world. Okay, so you have seen composition.